Welcome. This is, you could say, an extension of the already existing Mathematics 1 playlist on YouTube, which you all know. So the reason is that this topic of continuity and also differential calculus, in other words, derivative, has been missing last year. So this was sort of, due to reasons of time available, whatever. So it's an extension. You could also say it's an addition. And so it will be part of the Mathematics 1 playlist shortly. And it's recorded right now in a live session. And I will present you the solutions to these questions inside exercise sheet 5+6. It's called 5+6 because it covers topics of two different chapters of the lecture. Chapter 5 was about continuity as such, which is, by the way, a very important prerequisite for the question of differentiability of a certain function of one variable. And all of this is, since we are in the first semester, all of this is reduced to simple functional terms of just one independent variable, x. And the question of a limit existing, yes or no, is strongly correlated with the question of continuity. And then after, the focus will be on taking the derivative, using all the well-known rules of differential calculus with one variable. So let's jump into the first one, which is called exercise 5.1. What you see here are four different expressions, functions, which may have a property at a certain position to be discontinuous. And in order to find out, we will try and find the limits of these expressions at the given position, at the given value of x. So I just named them, sort of like, if we imagine that all of these terms do really have a limit value, which is a fixed number, I call these numbers capital A, B, C, and D, just to, well, not to mix them up. Also, a little bit below, I took my chance and generated some plots of these functions with the famous and very recommendable GeoGebra app, which you know probably. And then I called them lowercase a of x, b of x, c of x, and d of x. Let's talk about this a little bit later. Let's first of all look at the first fractional function here, which is relatively easy to be seen that this, well, first of all, that this rational function is a so-called improper rational function. What is this all about? Well, fact is that the numerator grade is equal to 2. You know what this is? The grade is the highest exponent that you find in this polynomial, while the denominator grade is obviously equal to 1. So since the numerator grade is not lower than the denominator grade, this is a so-called improper rational function. Actually, this is not even the point of interest here. The point of interest is, does this function behave continually if x approaches 0? And as you know, taking the limit generally means, usually if you have a limited value here, other than infinity, you have to check from both sides to be exact. Okay, so what do we see? Well, first of all, it just strikes you that the numerator term may easily be transformed to be what you see here. It's x plus 1/2 in parentheses and then squared. This is quite obvious that this is due to the first binomial, how do you say, binomial formula. Okay, so otherwise, if you don't see it, you might even use the approach of completing the square. This is what I did here, so please don't be confused by the fact that I wrote down -1/4 and then +1/4 and then crossed it out. This is just a method of completing the square. You might also see it with blank eyes. Okay, so what it means is that actually this function does have even a double zero at x equals -1/2. This is quite obvious, but even this is not the point of interest. The point of interest now is, look here, you see that there's obviously a definition gap at x equals 0. And this is why we ask for the limit of this function at this critical value of x, right? And this is what we would usually have to do from both sides. Now let me switch to the considerations below. First of all, you will see, or you see immediately that it's quite easy to split this fraction up. This is due to the fact that the denominator term is very simple. So you can just split it up. And what you find is that this is the same as, you look here, then you can see it still. X squared over x is to be shortened, and then we get x, purely x, right? Then plus x over x means +1. And finally, +1/4 over x, which is 1/4x. So this is a simplification of the term. Now it's quite easy to take the limit for x approaching 0 from both sides, which I denote by saying plus or minus simultaneously. You may use a different notation. It's not so important. Anyway, we find that this x term quite clearly approaches 0, so nothing interesting happens here. We just put it there, it approaches 0, while this constant +1 stays constant, it's equal to 1. And now the interesting term, this one is, you see, properly rational, right? That's the difference, because after switching to this form, what I've done actually is I have performed a polynomial division, actually. So this improper fractional function has been, you could say, transformed to a polynomial contribution plus a properly fractional contribution. And what we all know is, since here the numerator grade equals 0 and the denominator grade equals 1, this sort of function always approaches 0 against infinity. But now the question is, what happens if x equals 0 from positive or from negative values? And now, without a further argument, so this is because this is basic knowledge. Yeah, you could say this is also this is common sense, that sort of the reciprocal of x, of course, is divergent if x approaches 0, and of course also it approaches positive infinity in the positive case and negative infinity in the negative case. So it's quite obvious that this function approaches plus or minus infinity respectively when x approaches plus or minus 0. And now you see graphically, this is just a rough sketch. Since we argued before that there is a double 0 at x equals -1/2, this means there must be a touching point with the x-axis. Here you see it. I just made as I said, a rough sketch. What you also see, this is the black line here. This is obviously the so-called inclined asymptote, which always exists if your numerator grade is higher by 1 than the denominator grade. This is also common sense, basic knowledge, right? So that's the black line is the one which is, well, you could say that the graph of our function, you see it here in blue, it's a very bad sketch, I know. It approaches the black line if you go to the outside. Now, what do we see? Basically, we see that near x equals 0, we have a negative tendency here of our graph going to ever more negative values, and suddenly we have positive values on the right-hand side. So this is a so-called simple pole, okay? This is a pole, which means we have a true definition gap at x equals 0, which may not be removed. So this is a non-removable definition gap. That's it, right? And so we find out that this function is not continuous. It's discontinuous, which also means it will not be differentiable at x equals 0. So that's basically all it means. That was the first example, right? So the second one, I can, let's just have a look shortly at the more elegant sketch here, the blue curve, right? So it's the same thing, but more exactly, you see the same again. This is the graph A of x of our first example here. Now the second one is interesting because, but actually this is quite a difficult case, which you see latest when you look at the graph, at the plot generated by GeoGebra or other tools. The difficult part is this sign of 1 over x. So because taking the reciprocal here and then applying the sine function means that you have sort of a extremely non-linear, yeah, you could say, distortion applied to the periodic well-known sine curve, right? Because if x just simply increases, well, let's say it decreases normally, it just increases, and then you find that the reciprocal gets approaches ever smaller values, and so this is the reason for this high amount of distortion that the functional curve of this part well suffers, you could say. And then on the other hand, we have a factor of x here. So the question is, what happens taking the limit for x approaching 0 again? And now it strikes you that this factor of x quite simply approaches 0, of course. But now the problem or the question, first of all, is what happens here? Because if x approaches 0 at this place, we get sort of something, an argument which approaches infinity. And from looking from both sides, it's even approaching plus or minus infinity. So that's really a bad situation. Now, you could say the rescue argument to get through is stating that whatever this argument is, it stays bounded as long as x stays bounded. But more importantly, we all know that the sine function has a feature that it never produces values outside of the interval from -1 to +1. Okay, so this is why I denote the whole sine of 1 over x term be bounded. This is a very important argument, because just imagine this term. It could be the case that this is a term which diverges against, say, infinity. So then it would be a hard problem to judge whether the expression x times something else has a finite limit or has not. You see, because something of the sort 0 times infinity, just in quotation marks, it's not so easily decidable. It might be that the 0 dominates, it might be that the infinity dominates. And so in those cases, it's sometimes very hard to find the limit. But now, in this case, we have something which clearly approaches 0, x itself, and some other factor which clearly stays bounded. And that's a sufficient argument to say that the whole expression approaches 0, and therefore, from both sides, it approaches 0. Therefore, the graph of this function must be continuous at x equals 0. And now look at the graph, and you see what kind of a really sophisticated problem this is looking here, because this, as I told you, this extreme distortion of the sine curve. Also, what you see is sort of an envelope damping effect due to the factor of x. You see, this is the first bisector here, as we call it an envelope curve to the factor of x. This means that the value of the sine function is even rescaled additionally to ever lower values near x equals 0. But although you can't see it with blank eyes, it must be the case that the whole graph is continuous in the origin. And this is really not easy to understand and to imagine, of course. But now this is a clear proof that we have a limit, and which means we have continuity at this position. Now, about the before mentioned famous rules of L'Hopital, which I should perhaps write out here. I don't know, it's usual to call them the rules of L'Hopital. This is a French name, as you can see, and so it's written like hospital, but please pronounce it to be L'Hopital. These rules are very helpful, especially in cases. So this is not referring to this little sketch. It's especially in cases where it's hard to decide otherwise. Look at this fraction. You find that in the numerator, the difference 1 minus cosine of x, if again x approaches 0, is a term which approaches 0, right? Because the cosine of 0 equals 1, so 1 minus 1 is 0. On the other hand, the denominator again is x, which approaches 0 also. So the whole expression is of the sort 0 over 0. And this sort of situation is one of the famous ones which can, especially in difficult situations, which can be solved using the rules of L'Hopital, or let's say L'Hopital rules, whatever. I don't know how it's officially called in English. How to do so? And the problem, first of all, is it doesn't make sense to just say, now let's just set x equal to 0, and so we have 0 over 0, and we don't know what to do. Now instead, and this is, of course, due to a certain proof that was given by L'Hopital, in such cases, it can be shown, it can be proven that the behavior of such a function is the same as if you instead take the ratio of the respective derivatives of the numerator term alone and the denominator term alone. So please don't ever use the quotient rule or ratio rule from differential calculus at this place. Instead, you must differentiate numerator and denominator term separately. And this is what I do. It's quite simple. Look, this is a constant one which goes away by taking the derivative, right? And this is negative cosine of x, and the derivative of cosine of x equals a negative sine of x. So I get negative sine of x, which is positive sine of x in the end. Then in the denominator, I have my term, linear term x, which gets differentiated to be 1. And so all that remains is sine of x over 1. And now I'm done, because I see that clearly if x approaches 0, sine of 0 equals 0. But here I have a fraction line over 1, where the 1 is constant. And in the end, this means I get a clean case of 0 over 1, which is 0. And so it's not 0 over 0 anymore. It's simple. It's just a clean 0. And this is really a valid proof for the fact that this expression approaches 0 at x equals 0. And this is sort of my way of explaining why this is so. Now look, it's quite obvious that 1 minus cosine of x may be displayed graphically. And what do we find? We find this is sort of a negative cosine, you know, the cosine put heads and tails, or how do you say, heads over tails. So first of all, and then shifted vertically upwards by 1. So you may all follow me by agreeing that this blue curve is roughly what the 1 minus cosine of x would be graphically. Then, on the other hand, the x term corresponds to the famous first bisector, the linear function with an inclination of 1. So this is the orange line here. Now look, what happens if x approaches 0? It's very important to see that the blue curve approaches 0 much more quickly, you see, from both sides, than the orange curve, the orange line. So that's why you could say the numerator term dominates this limit procedure. It dominates because although the whole expression is of the sort 0 over 0, you could say the 0 in the numerator is stronger than the 0 in the denominator, because the numerator approaches 0 more quickly than the denominator. And that's why the numerator 0 dominates, and the limit of the whole expression is 0, although even the denominator approaches 0. So you see it graphically here. But the rules of L'Hopital make it clear, well, more explicitly and more formally. So I hope you got clear with that one. And now, is it that? Yeah, I think it is. And then for the last one, well, this is quite easy to be decoded if you have a certain experience with rational functions. What you see, first of all, is that this one is improper still, because the numerator and denominator grades are equal to 2. So this is a case where we have a horizontal asymptote, by the way. The interesting point, the point of interest here is x equals -2. And first of all, before starting to analyze such an expression, you should, of course, find its definition gaps completely. And it's quite obvious that the zeros of the denominator term are the definition gaps of this function. Of course, why is it? Because we may never perform a division by 0. So the zeros of the denominator are important. So now you can use the famous solution equation for quadratic terms. You can use the theorem of Vieta's theorem, which I've used. However you do it, completing the square, whatever, you find easily that -2 and +3 are the zeros of this expression. You can also insert and test. So it is easily possible to transform this to be the product of x plus 2 multiplied by x minus 3. Just perform this multiplication, you find exactly this quadratic polynomial. So that's no surprise. It means suddenly there is a definition gap at -2 and at +3. Both of them are definition gaps. Now, in this case, but I must say, it turns out that one of these definition gaps is a so-called removable gap. And the removability of such a gap is due to the fact that sometimes a 0 of the denominator term is at the same time 0 of the numerator term. You see? And now looking here, and this has been constructed in such a way that you can easily also find the linear, the product version of this polynomial, which is, it's easy to guess, okay? It's x plus 2 times x plus 5. Now you see, if you just remove the parentheses, 2 times 5 equals 10, then 2 plus 5 equals 7. So that's it. And you see that that's the important point. The -2 is a 0 of the numerator term, as well as a 0 of the denominator term. And that's why it can be shortened. And this is what we call a removable gap. And after we have removed it, it's quite an easy task just to let x approach -2, because we just fill it in, we just substitute it in the remaining term, and then we find the limit value. And also we find that there is no discontinuity at all at this critical position, because it's not critical anymore after all, right? I hope you understood what I'm saying. This is the product version of these terms. Here we can cross out, arguing that as long as x does not equal -2, because we approach it carefully, these are identical numbers, unequal to 0. We can cross them out. What remains are these two terms in a ratio form. So we just insert -2 here. We get -2 plus 5 equals 3, and -2 minus 3 equals -5. So the result is -3 over 5. If you wonder why this is, just look at the sketch or at the graph here below, and it's the red one where you see there is actually a definite gap at x equals 3. No wonder, because this hasn't been shortened away. So this is, you could say, this is a non-removable gap at x equals 3. A simple one, which you see by the fact that this is a pole position, not like in Formula 1 races. It's a pole with a sign change, of course, here. But on the other hand, at -2 for x, look here, the graph is just simply absolutely harmless. It just goes through here with an actual value of -3/5, which you can guess by looking here. Well, some people say it's not my taste, it's not so important, but as long as you haven't shortened and as long as you haven't removed this removable gap, you would be obliged to make such a circle symbol here to denote that this is, formally speaking, a definition gap, but after you successfully removed it and replace your function by this shortened term, you can just leave the circle symbol away. So that was it for the first exercise. Thanks.